Hi, my name is Sanskriti Singh, and my project is CheX-Nomaly, the segmentation of lung abnormalities from CXRs or chest radiograph X-rays using machine learning. Numerous models have been created to diagnose or segment various diseases from various biomarkers, but we rarely see them implemented in real time, since the risk of misdiagnosis can lead to one's death. It also has a drawback of the high cost of using many specialized models, especially because many of these models are trained on a specific disease. In an ideal world, we would need to run each of these models numerous times, which accumulates more money, more cost. To address this problem, researchers have begun to train models to predict and segment numerous diseases. However, this approach has the cost of performance on each disease, since multi-classification performance is theoretically lower than binary classification. Respiratory diseases are the leading cause of death globally and account for 50% of all deaths in the entire US. CXRs, or chest radiograph X-rays, are considered the gold standard for diagnosing respiratory disease. However, doctors and radiologists still claim that the high death rate is due to misdiagnosis on the CXRs. NIH states that around 60 to 80% of all these misdiagnoses happen because of perceptual errors, where the radiologist or doctor examining the scan is not able to locate the correct location of normality, meaning they're analyzing an inaccurate spot. In contrast, only 13% of these misdiagnoses fall under misclassification, the differentiation between disease. For this reason, it is more valuable for a model to be able to locate the abnormality within the image versus having better classification of the disease, since it addresses the larger 80% without leaving performance. I deciphered two different ways or two different approaches, both of which were novel, to create this model. First, I trained 14 different specialized models on specific diseases using a unit architecture, and then assembled the outputs together. And I exploited two different methods to do this. One was simply a max, and the other was taking each of these masks and feeding it to yet another unit model, which could potentially learn which masks are accurate, but which ones aren't. But this, unfortunately, was too random and was not able to learn anything. While these models performed well in its specific disease, it was not accustomed to the features of other diseases, which results in bad performance. In contrast, my second approach, the supermodel, the novel part of this project, overcame this problem. It was trained on all the data and paid no heed to class. It improved the performance by 95% in mean absolute error and 92% in focal loss. The goal of CheX-Nomaly was to be able to detect any kind of abnormality regardless of disease and to generalize its usage. So to check this, I tested my model on an external data set that contained diseases it had never seen before, including COVID, pneumonia, rib fractures, and more. It performed with a 0.03 mean absolute error, and upon the addition of attention, it improved by 33%. The final model beats the current state-of-the-art model by 32%. CheX-Nomaly is successfully able to aid in the precise diagnosis of location of chest disease, potentially saving lives and improving outcomes. Thank you.